I want you to try and imagine creating something incredibly durable,
Okay.
like something so perfectly stable that long after you are gone, this microscopic creation just continues to exist in the environment, completely unchanged.
Right. Unbothered by heat or water or just the passage of time.
Exactly. And, in a vacuum, that sounds like a massive triumph of material science. But when that infinitely durable creation is a synthetic chemical drifting through our soil and our water, well, that scientific triumph kind of morphs into a profound ecological crisis.
Yeah, it really does.
These are what we call forever chemicals.
And the irony is, the very trait that made these chemicals an industrial miracle for the better part of a century, their absolute refusal to degrade, is the exact reason they're now considered a global environmental threat.
Welcome to the deep dive. Today, we have a stack of sources detailing a major update on this front. It's centered around a May 2026 article by Adrian, published in Environmental Science and Technology, and also featured on technoscience.net.
It's a really fascinating piece of literature.
It is. And our mission today is to figure out if the bold promise of this research actually holds up. Like, have scientists finally found a way to destroy these indestructible pollutants without just, pouring a bunch of new harsh chemicals into our water supply?
Which is a huge deal because the scientific community has been wrestling with this supposedly unbreakable problem for decades now. I mean, the material we're analyzing today points to a genuine paradigm shift in the fundamental chemistry of how we approach these pollutants.
Okay, let's unpack this, because before we get to the how of dismantling them, we
Yeah.
really need to understand the architecture of the problem itself.
Right.
We need to know why they are so unbelievably stubborn.
Well, to understand that stubbornness, you really have to look at the atomic level. These forever chemicals are broadly categorized as PFAS, and their immortality relies entirely on how they are structured.
And our sources actually provide a great visual for this. It comes from the University of Nebraska-Lincoln. It's this molecular representation of a specific type of PFAS, perfluorocontained sulfonic acid.
It's quite a mouthful.
It really is.
Yeah.
But when you look at the rendering, you see this incredibly rigid carbon backbone running right down the middle. But that carbon core isn't exposed at all. It is entirely surrounded, like completely armored, by fluorine atoms.
Yeah, and that carbon-fluorine bond, that is the heart of the crisis. Fluorine is highly electronegative.
Meaning what exactly?
In simple terms, it aggressively pulls electrons toward itself. So when it bonds with carbon, it creates this dense, incredibly tight shield of negative charge around the carbon backbone.
Oh, wow. Okay.
It takes a massive amount of energy to forge that bond and, consequently, a massive amount of energy to break it. Normal environmental processes just don't stand a chance.
So like bacteria in the soil.
Bacteria can't process it. Sunlight under normal conditions just bounces right off. Water cannot penetrate that negative charge to dissolve the bonds. It is literally a microscopic suit of armor.
And that armor is exactly why human beings started manufacturing them in the first place. I mean, we wanted materials that could completely repel water and resist oil.
Unmatched molecular stability is a highly desirable manufacturing trait.
Right.
If you want a frying pan that refuses to let an egg stick, or, firefighting foam that can smother a jet fuel fire without instantly vaporizing from the extreme heat, you rely on those impenetrable carbon-fluorine bonds.
But because they ignore natural degradation, they just accumulate.
Exactly. They migrate from the factory to the consumer product into the soil, into the groundwater, and eventually into human bloodstreams.
And they are deeply embedded in completely mundane everyday life, too. Like, alongside the complex chemistry in our sources, there is this image of a snack advertisement that perfectly illustrates this.
Oh, the wafer wrapper.
Yes. It's for an Excello Bono Duo wafer. The ad shows this bright red, shiny, crinkly wrapper holding a chocolatey wafer. It even has this quirky marketing slogan, "Do you speak T9 Amish?"
It's basically a perfect representation of modern consumer convenience.
Yeah, but think about the engineering behind that crinkly wrapper. To keep the chocolate wafer fresh, and to prevent the grease from seeping through the packaging onto your fingers, the food packaging industry has historically relied on the invisible chemical shields provided by PFAS.
Right, because nobody wants a greasy candy wrapper.
Exactly. And we interact with this ubiquitous packaging constantly. You buy the snack, you tear open the wrapper, you eat the wafer in like 3 minutes, and then you throw the packaging away.
Yep.
The paper or plastic of the wrapper might eventually break down in a landfill, but those heavily armored carbon fluorine chains, they just wash right into the water table.
It's wild when you think about it. We engineer a chemical meant to last for an eternity, and we apply it to a disposable wrapper meant to be used for exactly 3 minutes.
It's so disproportionate.
That fundamental mismatch in lifespans is exactly what drives the current accumulation.
So if these chemicals are designed specifically to repel water and survive indefinitely, our standard municipal water filters must be completely outmatched when trying to remove them. Like, why can't we just filter them out like other impurities?
Well, if we connect this to the bigger picture, we really have to look at the analysis provided by Associate Professor Zhongshu Wei from Aarhus University. He actually led the new research detailed in our primary source.
Right.
And he highlights a critical limitation in how municipal water facilities and environmental cleanups currently handle PFAS. The industry standard right now relies heavily on activated carbon filtration.
Okay, and activated carbon works through absorption, right? Like, it's a highly porous material, so as the water passes through, the forever chemicals get physically trapped in the microscopic pores of the carbon.
Exactly.
So the water that comes out the other side is clean, but you haven't actually neutralized the threat.
No, not at all.
It's like wiping up a stubborn grease stain on your kitchen counter with a paper towel. The counter is clean, but you haven't destroyed the grease. You've just relocated it to the paper towel.
That is a brilliant analogy. The carbon acts as a highly porous sponge, basically taking the pollution out of a liquid state and trapping it in a solid state.
Which doesn't solve the underlying issue.
Right. You start with contaminated water, you run it through the system, and you are left with clean water alongside literal tons of highly toxic PFAS-saturated activated carbon.
Oh, wow.
And the disposal of that saturated carbon is an environmental nightmare. If you bury it in a landfill, the chemicals eventually just leach right back into the groundwater over time.
And what if you burn it?
If you try to incinerate it, standard commercial incinerators often just don't reach the extreme temperatures required to actually snap that carbon-fluorine bond.
So the chemicals just survive the fire, catch right on the smoke plume, and disperse into the atmosphere, only to rain back down on the environment later.
Exactly.
We're literally just shuffling the pollution around.
We're playing an incredibly expensive game of environmental musical chairs. Professor Y's point is that trapping them is just a stopgap measure.
Yeah.
We have to stop managing the location of the molecules and start dismantling the molecules themselves.
Okay, here's where it gets really interesting. The researchers at Aarhus University aren't just trying to catch the chemicals anymore. They are trying to shatter them.
Yes, they are.
And the tool they're using isn't a new synthetic acid or something. It is high-intensity ultraviolet light.
UV light.
Now, I have to push back on the mechanics of this a bit, because we just established that the carbon-fluorine bond is effectively a microscopic suit of armor. It resists extreme heat. It resists chemical attacks. Shining a bright light into a tank of water sounds far too passive to break a decades-long chemical bond.
And that skepticism is totally warranted if we assume the light is attacking the PFAS directly. But the mechanism of action here relies entirely on how the light interacts with the surrounding environment.
Okay, the water itself.
Yes. The researchers discovered that the breakthrough requires very specific high-energy wavelengths of UV light, specifically deep ultraviolet radiation under 300 nanometers.
So by blasting the water with those deep UV photons, you are essentially overwhelming the water molecules. Like, the photons carry so much pure kinetic energy that they physically shatter the H2O bonds, creating fragments that are violently unstable.
The technical term is a photolytic reaction.
Photolytic reaction, got it.
Right. The intense UV light forces the water to decompose into hydrogen radicals. And what's fascinating here is the sheer reactivity of a radical.
Because it's missing something, right?
Exactly. A radical is a molecule that is missing an electron. It's chemically incomplete. And because of that missing piece, it desperately seeks out another electron to stabilize itself. It acts with violent aggression to take it from whatever is nearby.
So the UV light essentially arms the water. It turns standard H2O into an army of molecular scissors that just start tearing at anything in their path.
That's a great way to put it. When those highly reactive hydrogen radicals crash into the PFAS molecules, they carry enough sheer chemical force to overcome the electronegativity of the fluorine.
Oh, wow.
They literally rip the fluorine atoms right off the carbon backbone. This specific action is called defluorination.
They are forcibly unzipping the chemical armor.
Precisely. And once you strip away those fluorine atoms, the incredible stability of the forever chemical just collapses. The shielded carbon core is exposed.
And then what happens to the core?
As the bombardment of hydrogen radicals continues, the once indestructible PFAS molecule begins to fragment. The long carbon chain snaps into smaller, simpler, and much less persistent compounds.
That is incredible. We are taking the very medium the chemicals are polluting, the water itself, and manipulating its physics to turn it into the exact weapon needed to dismantle the pollutant. No chemical additives required. So what does this all mean for the immediate future? Like, if we have the blueprint for breaking the armor, can municipal water treatment plants just swap their activated carbon filters for deep UV reactors tomorrow and clear out the water supply?
Well, the researchers themselves, including Professor Wei, are very quick to temper that kind of immediate optimism.
Yeah, I figured there was a catch.
There always is. This research represents a breakthrough in fundamental chemistry. It establishes a proven mechanism. But translating a chemical mechanism into a large-scale commercial utility involves some really significant engineering hurdles.
Like what?
First and foremost, the process of defluorination is currently quite slow.
Which is a major bottleneck. I mean, a municipal water plant processes millions of gallons of water a day. The water moves incredibly fast.
Exactly.
If this UV radical reaction requires prolonged exposure to fully dismantle the molecules, it just can't keep up with the flow rate of a city's water demand.
Right. The reaction simply needs more time than a fast-flowing treatment plant can easily provide right now.
Okay, what's the second hurdle?
The second major hurdle involves the actual breakdown process itself. When a long, complex PFAS chain begins to fragment under that radical bombardment, it doesn't instantly vanish into harmless elements. It breaks down into shorter PFAS chains.
So these are the intermediate compounds our sources mentioned.
Yes.
And if you chop a highly toxic, indestructible long chain in half, you don't actually solve the problem. You just create two slightly shorter but still toxic chains.
And in many ways, those shorter intermediate compounds present a much trickier engineering problem.
Why is that?
Because they are smaller, so they're much more mobile in the water table. Furthermore, if a treatment plant tries to use a hybrid system like running UV light first and then catching the rest with activated carbon, those shorter chains actually slip through the microscopic pores of the carbon filters much easier than the long chains do.
Wait, really? So a partial breakdown is effectively worse than no breakdown at all. If you don't drive the photolytic reaction to total completion, you end up creating a new suite of smaller pollutants that are even harder to catch.
Exactly. The environment has to be highly controlled to ensure total mineralization.
Man, that is a serious challenge.
It is, but this raises an important question about how we contextualize scientific progress.
Yeah.
You know, when dealing with an ecological crisis, there is this huge tendency to demand an immediate, off-the-shelf commercial product.
Right.
When a discovery like this comes with caveats about speed and intermediate byproducts, it is really easy to dismiss it as impractical.
Yeah, there's this expectation that a discovery only matters if it can be plugged into the wall tomorrow.
But profound scientific advancement requires foundational steps. I mean, before this research, our only viable strategy was moving the pollution from water into solid carbon blocks and just hoping we could find a safe place to bury those blocks.
We were entirely focused on managing the location of the problem.
Exactly. By identifying the exact interaction deep UV light under 300 nanometers, generating hydrogen radicals to strip fluorine atoms, science has finally uncovered a true, verifiable chemical engine of destruction.
We finally have the mechanism.
Yes.
So the next decade of research doesn't have to search for a solution from scratch. It just has to focus on optimizing the engine we've already found.
Precisely. Engineers can now focus on making the UV reactors more energy efficient, scaling up the radical generation to match municipal flow rates, and ensuring the reaction time is long enough to completely eliminate those intermediate shorter chains.
It shifts the entire global effort from a state of permanent management to a trajectory of eventual eradication.
It really does.
That is a massive shift in how we view the problem.
Yeah.
I mean, we started this deep dive looking at these incredibly stubborn, heavily armored carbon fluorine chains.
Yeah.
Chemicals that we casually designed to wrap around our chocolate wafers, completely ignorant of the fact that they would outlive us all.
Yeah, we assumed their durability was just an eternal curse on our water supply.
But the research from Aarhus University proves that they have a vulnerability.
They are not truly indestructible if you apply the exact right physical forces.
And the best part is, we didn't have to invent a dangerous new synthetic compound to exploit that vulnerability. We just had to learn how to manipulate the kinetic energy of light to weaponize the water itself, unleashing radicals to tear the pollutants apart from the inside out.
It's elegant in a way.
It is, The researchers are absolutely right to point out the current bottlenecks regarding speed and intermediate compounds. It's obviously going to take a massive engineering effort to get this technology out of the laboratory and into the city reservoir.
Undoubtedly.
But Adrian's article in Environmental Science and Technology was completely accurate with its framing. This research provides a very real glimmer of hope.
It provides the definitive proof of concept the world really needed right now. And, there is a deep underlying irony to this entire discovery.
What do you mean?
Well, think about it. We spent nearly a century building highly controlled laboratories to engineer these synthetic, heavily armored chemicals, arrogantly assuming we could create something permanent that completely defied the natural world.
Right.
And after all that industrial hubris, the ultimate mechanism to dismantle our indestructible creation turns out to be an extreme application of the most fundamental natural elements available to us, light and water.
Wow. Yeah, that is ironic.
It really forces you to wonder what other profound invisible solutions to our modern crises are just hiding out there in the basic physics of our natural world, patiently waiting for us to shine the exact right light on them.